This video is for Math 0242-1342 for sections 5.1 and 5.2. Chapter 5 is about probability. Many students have heard of probability in the past. It's taught as low as junior high, some of the basic stuff of it. Probability is a good way of thinking about it is what I call single or basic probability. And this actually goes back hundreds of years. They knew about this single or basic probability. They often write this capital P to mean probability, and then they'll put in the parentheses either like a sentence or a word or just even a letter, like probability of heads on a coin. Probability is good over total. So you want to count how many good things can happen to you divided by the total number of things that can happen. On a coin, there's two sides of the coin, so that's why the denominator is 2. And there's one good thing if you're trying to get a heads, so it's 1 out of 2. Probability can be written as a fraction or a decimal or a percentage. Generally, they prefer fractions. One nice thing is they often don't force you to do reduced fractions, so and especially on problems where there's multiple parts, it can actually be helpful not to reduce them. But probability always has to be between, and I can write it this way, probability of some event in general, just call it E for event. It's always between 0 and 1 as an answer. All probabilities are between 0 and 1. And this in math, when you put a double less than around something, that means between, right there, this part. But what this really is telling you is that it can't be a negative, because the lowest it can go is 0. It can't be negative, and it can't be bigger than 1. So sometimes they have questions like, which of the following is, or which of the following is not a possible probability answer. So you'd be looking for anything that's negative, anything bigger than 1, those cannot be. Fill in the blank. Okay, if an event cannot occur, its probability, see, this is kind of what I was just mentioning. The lowest it can go is 0, so if something cannot happen, it has a probability of 0. In fact, it can't even have an answer of -1 ever. And it could be 0.5, but not always. And then if it's guaranteed to happen, then it has a probability of 1. So if you ask 5 people a question, are you going to vote for candidate X? 0 out of 5 might say, yes, I'm going to vote for that person. 0 out of 5. 0 divided by 5 is 0. That's the lowest it can go. If all 5 of them say, yes, I'm voting for that person, 5 out of 5 is 1. That's the highest it can go. But usually it's somewhere in between. Okay, there's common things they do with probability. One of them is to roll 1 die or roll 2 dice. Die is singular, dice is plural. If it's a single fair die, then it's going to come up 1 through 6. And this is what's called sample space. Sample space in probability is when you list every possible thing that can occur, like heads or tails. On a coin, the sample space is literally heads or tails only. And then that's why in flipping coins, the denominator is always a 2. But in rolling 1 die, the denominator is always a 6, at least prior to any possible reducing if you want to reduce. So one thing I do is I always put the total down right away just to make sure you don't forget that. Because there's students on tests that they're supposed to get an answer of, let's say, 5 over 6, and they only put the 5, they don't put the over 6. So it seems like they're making a minor mistake, but it's actually a major mistake in probability because the answer literally cannot be bigger than 1, and they're somehow getting an answer of 5, which doesn't make sense for what's possible. So put your total down first so you don't forget about it. There's 6 things here. If they ever list the sample space, or if you can know what it is, then it's often easy to just count how many are here. Sometimes it's too large to list it though. And then the other nice thing about having the sample space is then I can see every individual entry and I can count up how many of them are good, how many are considered a success. It depends what we're trying to find. We're trying to find the probability of getting a 4, just a 4. There's only one 4 in this list. So this is right straight out of basic or single probability. I'm just trying to do one single thing. All I want to do is roll one die and get a 4. That's one thing. It's a basic probability, so I'm doing good over total. There's one good thing out of 6 total. It's kind of like 1 out of 2 for a coin. So at least there's not a lot of heavy math in this chapter, but it's very common that people make little mistakes or miss important details. So we're still rolling a fair die. The sample space is still 1 through 6, so no matter what question they ask me, there better be a 6 in the denominator. Before, all they wanted was a 4. Now they want a number greater than 1. Well, 1 is not greater than 1, but 2, 3, 4, 5, and 6, all the other 5 numbers are greater than 1. So this is 5 out of 6. Okay, then you can have a little chart formed here. And in the chart, there's a column of whatever this problem's about. Here it's flipping coins, obviously, with heads and heads, heads and tails, tails and heads, tails and tails. And then the second row or column is the probability. And these kind of problems, what they ask you here is the given a probability model? Is this a proper probability model to have, like, to list every possible case? If you flip a coin twice, there's only 4 things that can happen, actually. It's either both heads, both tails, or a heads first or a heads last. You can get one heads by having it come up first or last. These are the 4 possibilities. In order to say yes to this problem, there's 2 things that you need to check on the probability column. Is each individual probability between 0 and 1, because that's a hard rule right here. Probability answers have to be between 0 and 1 no matter what, individually. Well, 0.37 is between 0 and 1. 0.93 is between 0 and 1. So is 0.03. But this is a big rule violation right here. Probability cannot be negative no matter what. So this is not a probability model. There's a mistake in this model. There should never be a negative in a probability answer. Now the outcomes, sometimes the outcomes are listed as numbers like how many people are going to vote for a candidate. And it could be 0, 1, 2, 3, 4, whatever. Those numbers sometimes can be negative, actually. They're often not negative, but they could be negative. In fact, a lot of these probability models model what happens in gambling games. So if you go to a casino or if you're into sports gambling, and the first row or column can represent how much money you win in the game. In many gambling games, people lose money. People lose money more than they win in the long run. Otherwise, all the casinos would go out of business. So they set up the games to make sure that they win in the long run, and then they don't care when somebody wins big in the short term because they know in the long run they're going to make all that money back. And in those, the X's, the first columns, can be negative. So just watch it. If you see a negative, doesn't mean it's automatically something wrong. But probability cannot be negative no matter what. This is definitely a no. Now, in another textbook I use, when you say no, they force you to say, why is it no? This is actually violating 2 different rules. Probability has to be between 0 and 1. So in other words, that's kind of a 2-aspect rule. That's telling you both that it can't be negative and it can't be bigger than 1. Now, we didn't have any that were bigger than 1, but see all these 0 point, 0 point, 0 point. If one of those was like 1 point or 2 point or 10 point, then you would have another violation of this rule, basically. But one of the individual probabilities is negative. That's bad. We already know the answer is no. But another rule, because those could all be positive, another rule is if you add all the probabilities together, like 0.37 plus 0.93 plus 0.03, and even if I hit minus 0.36, it's not supposed to be negative, but even if I add it up as a negative, another rule is that all probability in one model has to add up to 1 exactly, not just close to 1. This is close to 1, but you have to equal 1 exactly. So this is actually violating 2 different rules. I have an individual probability that's negative, and that's definitely no good. And the sum of all the probabilities doesn't equal 1 here. So this is really a double no right here. Okay, how probable is it? Someone computes the probability of several events. Probabilities are listed below. Select the best verbal description. So the probability of 2.08 indicates blank. See, that's impossible. Probability can't be 2.08. That's what I was just talking about. It has to have 0 point something if you're going to write it as a decimal. Probability cannot be negative no matter what. The probability can't be negative. The values can be negative, but probability cannot be negative. And it can't be bigger than 1 either, which is why if you write it as a fraction, you can never have the top of the fraction bigger than the bottom. So this is an impossible probability, really. Somebody made a mistake because it literally can't happen. There was actually a famous AP exam for statistics. The statistics course has an AP exam in high school. And they had a famous multiple choice question there one time where they did something like this, where the probability was like 2.08. And what the scenario was, it said that some college hired a professional statistician to calculate the probability of students doing well on an entrance exam. Say you get a really high SAT or ACT score. What's the probability that if you do well on one of those tests that you also get like A's in college? Because there's actually been studies done to show that those are not actually very good measures of how successful in college you'll be. There's people that get really high SAT and ACT and then they fail out of school. Other people get really low SATs and somehow manage to get into a college and then they succeed really well. So that was where the problem came from. And it said they hired this statistician and he calculated a probability of 2.08 for doing well on the exam and then doing well in college. The probability was supposedly 2.08. And then they said, what should the college conclude about this probability? And it was a multiple choice, and the choices were like, they should conclude that doing well on the SAT means you're going to do well in college. That would be true if it had like a high probability. And then another one said they should conclude that doing high, or well on the SAT means you're going to do very poorly in college. That would be if there was a low probability answer. And then another one said doing well on this entrance exam gives you about a 50-50 chance of doing well in college. That's kind of when you get a middle probability. And then the funny thing was the last choice said they should fire this statistician. And a lot of students read that question. They're like, why would that weird answer be the answer to this? So that oftentimes in multiple choice questions, there's like a choice you can just cross it out and say, oh, there's the obvious wrong answer. So like more than 90% of students crossed that one out and didn't even consider that could possibly be the answer. And not only was that the answer, that was the whole point of the question was, all that question was measuring was, do you know the range of probability answers? They have to be between 0 and 1. They can't be 2.08. And a real paid professional statistician, this is such a basic rule that a real statistician would know that. If they somehow, anybody could make a typo in their calculator or miscalculate something. But a professional would say, wait a minute, I did something wrong because literally the answer can't be 2.08. And if some college hired them to do this and they made such a gross mistake and didn't even realize it was wrong, then I guess they do deserve to be fired. So yeah, somebody made a mistake here. If it literally cannot be 2.08. There's nothing wrong with making a mistake, but if you try to pretend there is no mistake on a basic rule like this, then you're crossing the line in terms of your professionalism. But see, this is the middle one. If you're around 50%, then you've got like a 50-50 chance of it happening. So certain to happen is when it's close to 1. Unlikely to or cannot happen, that's when you're 0. Unusual is less when it's low, like 0.01 or something like that, something really low. Very likely to happen, but not certain is when you're like in the 90%. The event may happen, but is not likely. Maybe that's like 20 or 30%. But it's this one right here. The event is as likely to happen as not. If you're a 50% chance, you've got a 50-50 chance it's just as likely to happen or not. If it equals 1 exactly, remember it can equal it exactly. Remember I put equals under there, right? There's the equal sign. And right there, you can equal 0 and 1 exactly. And if it literally equals 1, then it's certain to happen. It's guaranteed to happen. If there's a 100% chance of rain, it's supposed to be guaranteed to happen. Now, sometimes that happens in the weather report. They say there's a 100% chance of rain and then it doesn't rain. Well, then they messed up and they shouldn't have said it was 100%. They should have said like 99. And often you see where they hardly ever say 0 or 99. There's like right now, if you check the weather report, it's got like 1%, 5%, 2%. It's got really low percentages every day. And it's probably not going to rain, but they rarely put 0 because you have to be absolutely certain about that. A probability of 0 means it's impossible to happen. It cannot happen no matter what. So these are the two extremes of probability. A 1, it's guaranteed to happen. 0, it cannot happen, but most probabilities in between the two. 0.87, that's when it's very likely to occur, but not guaranteed. It may happen, whereas it's very likely to happen, but not completely certain that it will happen. Or the other side of the coin is 0.18. This is where it's likely not to happen, but it still could. It may happen, but it's not very likely to happen. Negative's another impossible answer. Somebody made a mistake. Can't be negative no matter what. And 0.02 is an extremely low probability. So this is that other one I was reading. Very unusual. This is just that it may happen, but it's not likely. That's the 0.18. But this is unusual for this to occur. If there's only a 2% chance, if they told you there's a 2% chance of rain and then it actually rained, you'd be pretty surprised about that. So this is a good question just to get a feel for how probability ranges between 0 and 1, and which answers can even happen and which ones are higher chances, lower chances. Okay, during a recent season, pitcher Clayton Kershaw threw 2,500 pitches. Out of these, there were so many fastballs, changeups, curveballs, and sliders. What is the probability that he throws a changeup? So notice it's just one thing, just a changeup only. And we know there were 25 changeups. We know the good cases right here. But the answer is not 25 because that's bigger than 1. People on tests all the time, people tell me this answer is 25. And they're technically half right, but it's a major mistake that they're making because it literally can't be 25. It can't be bigger than 1. You're only doing the good, you're forgetting about the total. It does say round to 4 decimal places. So sometimes they force you to put fractions and they count decimals wrong. Sometimes they force you to do decimals and count fractions wrong. So we just have to read what they want here. The issue is I don't know the total. Oh yeah, I do know the total right here. Okay. So we know I thought we didn't know the total. And if we don't know the total, we could add all these other ones up. If I add up 1275 plus 25 plus 375 plus 825, this is where the 2,500 is coming from. But sometimes they're nice enough to tell you that, and I almost missed it. So it's 25 good cases divided by 2,500 total cases. And you're supposed to round this to 4 decimals, but this is going to come out exactly to 2 decimals. It's a 1% chance. 0.01 is 1%. But put it in as a decimal. 1%, 0.01. Now, it says, what's the chance that he throws a breaking ball? Now, if you're not into baseball, that's a curveball or a slider. Again, it has to be over 2,500 no matter what. Ors, typically you're adding something in an OR case. In fact, junior high kids, when they do basic probability, they're given OR problems. Other than the fact these numbers are very large into the hundreds and the thousands, if they put these down as like single digit or maybe double digit numbers only, then a junior high kid could do this problem. Because you just add the 2 cases, curveball or slider. Add the curveballs, 375, and the 825 sliders. So if there's an OR and both of these things cannot occur at the same time, then you just add them up. There's 1,200 of both of those, and we know the total's 2,500. So there's a 0.48, a 48% chance of him throwing one of those two pitches. So this is what I call a basic probability, and then this one's an OR, which is also known as a union. A Nevada roulette wheel has 38 pockets. 18 of them are red, 18 are black, and there's 2 greens. They spin the wheel, and a ball lands in one of the pockets. And all 38 of them are equally likely. What is the probability that you land in a green pocket? Round your answer to 4 decimal places. So there are 18 red, 18 black, but there's only 2 green. There's 2 green out of 38 total. 2 out of 38 is your chance to land in a green one. And round to 4 decimals, so 0, 5, 2, 6. There's a 3 after that. So keep this 6 as is, 0, 5, 2, 6. And remember what I said earlier about in casinos, they win money in the long run. They make sure that they win money in the long run. And that's why if somebody pulls the lever and wins $1 million, a ding, 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 and everybody's screaming and yelling, they actually like when that happens because it makes everybody else around them excited, and everybody's like, I want to be that person that wins $1 million. So it makes other people play more, and the more people play, the more money they make. And how does that happen? This is a very good example of how this happens. If this was a fair game and you could win as often as you could lose, then there should only be the red and the black. Then it would be a 50-50 chance to win. But here's how they make sure they make money in the long run. They add 2 green ones that everybody loses if those 2 come up. If you want a red, you can bet red or black. They don't let you bet green as a color. You can bet them individually, but not as a color. And you bet red or black. So you bet $5 on red or black and you win, you get $10, you double your money. But if you do it in the long run, you're not going to win half the time. It comes up only 95% of the time do you get one of the 2 colors. So that means about 47% of the time you win by betting red or black. So if it was a fair game, you should win 50% of the time, but you only win 47% of the time. And see, that little 3% is what guarantees the casino money in the long run. If you bet on green on every spin, you will lose more than 90% of the time in the long run. See, this is what casinos are built to know. Explain why this is so. Round your answer to 2 decimals. Okay, if you bet, you will lose more than 90% of the time in the long run if you always bet on green because you only win 5% of the time. So I actually should write this down for you here. There are 5 types of probability. We've learned 2 of them so far, and they're hinting at a 3rd one right now. The first one's called basic or single probability. Some people call this classical probability because it was done hundreds of years ago by gamblers that were gambling on games and cards and dice, and some wrote books. Actually, they realized they could make more money writing books and teaching you how to do it rather than doing it themselves, because when you gamble in the long run, you're going to lose in the long run. This is the one I already talked about, good over total. You just try to do one thing and it's good over total. Well, there's a second one called a complement. This is an opposite. This is the probability that something does not happen. It's technically bad over total. You can actually calculate it directly sometimes. Or it turns out, since these 2 are related to each other, you can get each one of these by doing one minus the other one. If I want the probability of an event to happen, and maybe the good over the total is complicated to figure out directly, but you already know the answer to the other one, you can do 1 minus that it doesn't happen. 1 minus that something does not happen equals the chance that it does happen. or the probability that something does not happen is 1 minus the probability that it does happen. And that's what they're doing here. We just got this 5% chance of betting on green and winning. So what's the chance that we don't win? If you turn this into a negative and add 1, so that way you're basically doing 1 minus it. If there's a little more than 5% chance you'll win betting green, that means there's more than a 90% chance you're going to lose betting green. 94%, almost 95%. That's literally what they just did on this problem. And then the third one you've learned too, the one's called unions, which are OR probabilities. These generally you're adding, but sometimes they're a little trickier than that. And then we'll eventually get to 4 and 5, or the last two types. There's an intersection. These are AND probabilities. Like, what's the probability of flipping a coin and getting a heads and rolling a dice and getting a 6? And then there's one called conditional. And there's usually a magic word that goes with this too, called given. Given that I rolled a dice and got a 3, now you try to roll the die and get a 4. But given that I already got the 3 the first time it happened. We'll get to these other two in a second here. So if you just do 1 minus this 0.05, that shows why it's more than 90% of the time. It's the law of large numbers is when you do an experiment many, many times, the probability that you'll settle on is what the actual probability is. In other words, if I flip a coin 10 times, we know that coins come up heads 50% of the time. But if you only flip it 10 times, that's a small number of attempts. You might not get exactly 5 heads out of 10 flips. But if you did 1,000,000 flips, even if it's not exactly 50-50, it's so close to 50-50 that it seems like you're hitting 50 on the dot. This is not about doing it a whole bunch of times. Well, maybe it is if you bet on green every spin of the wheel in the long run. See, this is about the law of large numbers, because the percentage times you will lose will approach, how many decimals? 2? Whoops. 95%. Since it's actually 94.7. So if you move this decimal over twice, 94.7 and then 95%, unless they want 2 decimals after that, 94.74 maybe. I think that's what they mean by 2 decimals. They mean 2 decimals in the percentage itself. So that's called the law of large numbers. If you do something many, many, many times, the percentages that happen to you in your sample start to approach what the real percentages in the population are. If you flip a coin 10 times, you might get 7 heads or 3 heads or 4 heads. Then the percentage seems like it's only 30, 40, or 70. But if you do it 1,000 times, you might not get 500 heads and 500 tails, but even if you get 498 heads, 498 out of 1,000, it's not exactly 50-50, but it's really close to 50-50. And 1,000 still not all that large of a sample. If you did it 1,000,000 times or even more, it gets even closer. So that's what this problem's talking about right here, this number 7. Okay, I'm glad this came up just now because I have it over here. The only downside to this number 3 one right here is that people go back to junior high when they're in college, and they always want to do the junior high version of this, but that's actually the exception to the rule here in college. There's 2 versions of this formula. If you're doing the probability of A or B, go to a high school, try to get a freshman or a female. It's not always as simple as freshman plus female. It might be probability of A plus B. But it can also be probability of A plus probability of B. So you always do the adding first. You're always going to add for sure first, but sometimes there's something to subtract. The probability of A and B. Oops. Ran out of room there. Probability of A and B. Okay, so there's a concept called mutually exclusive. That might be the next question. Let me see if they have that next. The event A does not occur. Oh no, right, this we talked about this too. Given the event A, the event that A does not occur. See, that's what I had. That's the second type right here. That's called a complement. Not something happening as a complement. I was thinking maybe they would do the mutually exclusive idea, but maybe it's coming up next. I guess not. But there's usually the textbooks have these problems where they ask you, here's a scenario, and yes or no, is it mutually exclusive or not? And now I got a spinning wheel, and when it does this, usually it never comes back. Okay, I'm going to have to close this, which means I'm going to lose my work done already, but hopefully we can remember which problems we did already. Whenever I close and reopen it, it resets me all the way back to the beginning. Luckily for you guys, it saves your work, but now I lost all my green checks for getting these earlier ones right. We did that one. I was skipping this for a reason. This is the complement rule. And I was hoping to see if they had about mutually exclusive. Here it is, see, well, except it's not the kind I'm thinking of. This is it, here, this is what I'm looking for. They really should move this problem up to the beginning of this section. So somebody named Benson earned an A in his history class in one semester, and he earned an A in his statistics class the same exact semester, and it's the same exact person. Mutually exclusive, the tricky part to it's not hard to work with, but the tricky part to it is it has a negative in its definition. Mutually exclusive this is when you cannot be both things, whatever they're talking about, both items, both things, both at the same time. Take my example for a second. I said we wanted to find a freshman or a female. Ask yourself, can you be both of those at the same time? Can I be a freshman in high school or college and a female at the same time? Yes, there's a whole bunch of them. So then the answer is no, they're not mutually exclusive because of the negative in the definition. It's always backwards from the way you'd think it would go. Can you be a freshman and a senior in a high school or college at the same time? No. So then yes, that is mutually exclusive. So the reason this is important is right here, these two formulas. You can only do the junior high easier one if they're mutually exclusive. If they're not mutually exclusive, then you have to do the more complicated one. So freshman or senior is mutually exclusive because you can't be both at the same time. So the probability of a freshman or a senior, you just add the two things together. That's kind of what we did here. Where was that one that had an or in it? Guess I didn't write it down anywhere. What was the one we had that was or on the dice? Or was it dice? No, it was the roulette, the color. No, the change-up, the pitches. Remember how there was one about just throwing a change-up, and then there was another one that wanted the breaking balls, the curve balls, or the sliders. Curve or slider. Well, a pitcher can't throw two different pitches at the same time. So curve balls and change-ups are mutually exclusive. And if you want to do an OR for that, then you just add the two together. That's all I did in that problem, was add them up. But now we're starting to get cases that you can be both at the same time. If I try to do freshman or female, it's not as simple as adding freshman plus female. You do that first, but then there's something to subtract. In this example, Benson earned an A in his history class. Usually people that get an A in one class, it may be that that's their subject they're really good at, but it's going to have some kind of effect probably in his other classes. If he's a good student, he's probably getting high grades in every class, and students that fail one class are more likely to fail others. So could he get an A in both classes at the same time? Yes, so then this is not mutually exclusive. The only reason I'm doubting myself now is that these are different subjects, so... But I think it's because it's the same person twice. His ability in school can affect both of these, so I would say this is not mutually exclusive. Yeah, okay. I didn't really like this example. I like the one, let me try another one, see if they got a better one. Like freshman or female, that's a little easier to see. This is better. At least 10 of the books are mysteries. At least 10 of the authors are male. So if you go get a book out of the library, could it be a mystery book or not? And could it be written from a male author or not? But could it be both? Could it be a mystery book written by a male writer? Yes. So then no, these are not mutually exclusive. And when they're not mutually exclusive, then this OR formula is not so easy to do. The general addition rule states that probability of A or B, it's A plus B, everybody knows that, but then you have to minus A and B if you can be both at the same time. And if you can't be both at the same time, then this has a probability of 0, and that's how the other formula, the one they teach in junior high, you're really using this formula every time, but the one in junior high is when this extra part at the end equals 0, and if you ever do something minus 0, it's equal to the something. So the back half of this formula disappears if you can't be both at the same time. So this is just knowing the formula right here. Then they make me apply it on this problem. So find the probability of A or B. Well, you're supposed to do the probability of A, 0.51, plus the probability of B, 0.8. Now here's something that happens. Some students are really troubled by this subtracting something because it's so ingrained in their mind that they were taught in junior high to ORs, you just add stuff together and there's nothing else to do. So that's a little bit of a disservice when we teach junior high kids that, but they're not ready for these harder problems is the problem. And I get people still to this day in college, and anytime there's an OR problem, all they do is just add the two things up, and it doesn't even occur to them that there could be anything else to it. And yet, if you do that here, we'll watch what happens when I press equals. I'm going to get an impossible answer right here. And that doesn't bother them either. On their test, they'll literally put 1.31. And they say, well, it said OR, I'm supposed to add them up. But remember, probability can't be bigger than 1. And the reason why this one's bigger than 1 is you can be both of these at the same time. These are not mutually exclusive. And what's happening is the part that can be both is 47% of both. If you don't subtract it, then you're double counting the ones that are both. Some people are freshmen only and not female. Some are female and not freshmen, but all the ones that are freshmen and female, you're double counting them if you don't subtract that part. And if you double count things, that's how you can go over 1. So if I subtract this 0.47 right here, now it's not an impossible answer anymore. And it would be wrong if I didn't do that. Sometimes when you add the two and there is something that needs to be subtracted, sometimes it's not an impossible answer at that point. But sometimes it actually is, and that could be a reminder, oh, wait a minute, I got bigger than 1, I must need to subtract something. So then they ask here, is this a case of mutually exclusive or not? Well, it would not be mutually exclusive if adding A and B equals the OR answer. If 0.2 plus 0.2 equals 0.3, that means there's nothing to subtract, and that means they are mutually exclusive. But clearly 0.2 plus 0.2 doesn't equal 0.3. 0.2 plus 0.2 is 0.4. So if the sum of A and B, like that other one that went over 1, if the sum of A and B is larger than the OR answer, 0.51 plus 0.8 is larger than this 0.84, and that's because there's something to subtract. And if you have to subtract something, it's not mutually exclusive. So 0.2 plus 0.2 is 0.4, then I have to subtract 0.1 to make it come out to 0.3. So that means these are not mutually exclusive. You can be both at the same time here. Okay, this is their symbol for complement. See how there's like a capital C as an exponent? So different books do this differently too. Some books do this, probability of B complement. So what this really means is the probability of not B. And you can find that by doing 1 minus the probability of B. Some books write B with an apostrophe. I've seen that before. Some put like a bar over the B. All these mean the complement, the chance that something won't happen. A good example of complement is rain versus no rain. If there's a 20% chance of rain today, then what's the chance it won't rain? Well, you have to do 1 minus 0.20, and that's how you get 0.80. So together, a normal probability plus its complement, they always add up to 1. 0.20 plus 0.80 is exactly 1. So any event you want to do, probability of a heads, probability of rolling a 4, probability of getting a freshman or a female, any individual probability you want to get, the complement is always 1 minus it. Or vice versa. If the complement's 0.4, if there's a 0.4 chance that it won't rain, then what's the chance it will rain? That's what they're asking here. If probability of B complement's 0.4, what's the probability of regular B? That's also 1 minus. So if you 1 minus either one of them, you get the other one. 1 minus 0.4 is 0.6. Okay, we're almost to the end of this now because I did get the first 7 right before it froze up. Let me give you the magic word of this second video of this unit. And it's going to be the same theme if you remember the last one. And I gotta make sure I remember what the last one was. I think I remember it now. Okay, so let's do the dash. Houston dash is the magic word of sections 5.1 and 5.2. Okay, this is good. I like these problems that have a chart given like this where there's a category on the side and a category on the top. Is 15 like this too? Yes, and this one's even more complicated. So take this as this one's good because it's got nice small numbers at least. I don't think we need the textbook here today. Okay, so we've got, you can have a runny nose or not. And you can have a sore throat or not when you're sick. And they just collect data from a sample like 6, 8, 3, 5. Usually in my in-person classes, I make on tests like this with smaller numbers because when you do these ginormous ones, then sometimes you will miss it just because of miscalculations, where just because the numbers are so large. But here, these numbers are nice and small. What I always do before I even read what they want me to find, I like to get the row and column totals. 6 plus 8 is 14. 3 plus 5 is 8. Notice that 14 plus 8 gives you a grand total of 22. This will be the denominator of every answer then, no matter what. They always put the total in the denominator. That's why I always like to know that first. Now do 6 plus 3, 9, and 8 plus 5 is 13. Notice that 9 plus 13 is also 22. 14 plus 8 and 9 plus 13, they're both 22. 22, 22. Don't put 44 here. I've seen people do that before. Then you're double counting everything, which is really bad. So the grand total is 22, not 44, but double check, because sometimes they get 22 this way and then they add this, they do this one and don't add it up. Maybe it's 23 this way. Anybody could have a slight adding error, and if you just misadded accidentally and didn't check the other one, then maybe you're going to get every answer wrong just because of a simple miscalculation in your head or typo in your calculator. Okay, so at this point, I don't think we're going to see those other two probabilities yet. I think this is only 5-1 and 5-2. So we'll have to add to this list later. This homework does not have these last two types of probability yet. They're going to be covered in 5-3 and 5-4. So right now, all we're doing is basic or single probabilities, good over total, complements, which are not something happening, bad over total. And each one of those can be found by doing one minus the other one. And then unions are ORs, but there's two cases of ORs, the mutually exclusive junior high case or the not mutually exclusive college level case. If you get an OR on a test in this class, it's much more likely to be the second one than the first one. But sometimes you get the first one. So here it says, find the probability that a randomly selected student has a runny nose. That's just a single thing. Just a runny nose is all we want. That's a single or basic probability. It doesn't say not, it's not an or, and it's not an and or a given. Those that we haven't even learned yet anyway. But all we want is a runny nose. So that has to be over 22 no matter what. Probability of a runny nose is definitely something over 22. That's why I like to get the total first. And runny nose is right here. Some people that got sick and got a runny nose also had a sore throat, but sometimes they don't. Maybe they just have allergies and their nose is running, but they're not really sick. So there's 6 that also had a sore throat, and there's 8 that also did not have a sore throat. But there's 14 total people that at least have a runny nose. So what I normally do is just leave this like this because there's multiple parts here. There's 4 parts of this problem. And if you start reducing fractions, you can if you want. If you divide both of these by 2, you get 7 out of 11. If you change it to a fraction, a decimal, whether it's 14 divided by 22, 6363 repeating, or 7 divided by 11, 6363 repeating. In general, it's not wrong to do these two things right here. But many times they'll take the unreduced fractions, so I would try that first. I guess I can't because I'm going to try it anyway. I was going to check this answer. Apparently they won't because it won't even let me put a fraction. But anytime they want fractional answers, they sometimes don't make you reduce them. So I would try that first. But this says round to 4 decimals, so it's not even giving me an option to put a fraction. So 6363, but there's a 6 after that, so you got to add 1 to this 3 and make it a 4. 6364. 6364 to 4 decimals. Now, find the probability a randomly selected student has a sore throat. There's another single probability right there. Sore throat is this way, though. So sore throat is 9. 9 out of 22. Probability of a sore throat is 9 out of 22. And apparently they only want decimals here, so 9 out of 22 is 4091. Bump this 0 up to a 1 because there's a 9 after it. 4091. 4091. So here's the best question of this whole problem. Find the probability a selected student has a runny nose or a sore throat. People are going to go back to junior high and say, oh, okay, I just need to take these two answers and add them together. 6364 plus 4091, and then it doesn't bother them that that's bigger than 1. Probability can't be bigger than 1. Something's wrong if you leave that as your final answer. And the reason why is you can have both at the same time. These are not mutually exclusive. You can have a runny nose and a sore throat at exactly the same time. In fact, it's more likely probably to have both than to just have one, because when you get a runny nose, it sometimes causes a sore throat. So the problem here is I'm double counting something. See, watch this. I like to do this with checks. The runny nose, where did this 14 come from? When I did 14 out of 22 for runny nose and 9 out of 22 for sore throat, that's actually 23 out of 22. That's why it's bigger than 1 as a fraction. It's 23 out of 22. So where did this 14 come from? That was the 6 plus the 8. That's how you got 14. That's where this 14 came from before I turned it into a decimal. Where did this 9 come from before I turned it into a decimal? The 9 was the 6 and the 3 is how you added up to 9. So notice this box is only checked once. This box is checked once, but I'm double checking this box. The people that have both a runny nose and a sore throat, I'm double counting those 6 people. So you know this formula, A or B. Your ORs you're always going to add. So the A, I'm going to do this in fractions first. The A is 14 out of 22. And the B is 9 out of 22. You're definitely going to do that as the first step no matter what. And sometimes that's all you do. If you can't be both at the same time, that's all you do. If you do the curveballs and the sliders, that's all we did. We just added them together. Because those you can't be both at the same time. But since I can get both a runny nose and a sore throat at the same time, then you need to subtract the chance of both, which is this box that's been double checked. Whenever you want both of them, you just go to where they meet each other in the table. Or another way of thinking about it is if you're subtracting 6, subtracting gets rid of one of the checks. So now every box that's been circled has one check only. And I would do this in fractions first. 14 out of 22 plus 9 out of 22. At first, that's 23 out of 22, which is an impossible answer. But as soon as I subtract 6 out of 22, the final result is not an answer that's impossible. 17 out of 22 could be the answer. In fractional format, if the top is smaller than the bottom, that's a good probability. 17 divided by 22 is 7727. And that's less than 1, so that's good. 7727. Find the probability that a randomly selected student has neither a runny nose nor a sore throat. So those are the two nots. But you could certainly have both of the nots. In fact, most of us that are not sick or having issues with allergies don't have both of these. Probably 90% of a year you're not sick in any way, and you don't have either one of these. So the ones that do not have a runny nose, see, circle that, that's 8 out of 22. Or, nor is another word for or, except it was when you were hoping they're not happening. So, or that you do not have a sore throat, that's 13 out of 22. Now, see, if you added this one up, it would be 21 out of 22, and then you might not realize anything's wrong with it because that's not an impossible answer. So anytime that there's something that needs to be subtracted, there's not always a warning that, oh, wait a minute, this is an impossible answer right here because this is already bigger than 1. That sometimes happens, but not always. But notice the knots, I added 3 and 5 to get 8, and I added 8 and 5 to get 13. That's where the 8 and the 13 came from, but I'm double counting these 5 right here. The 5 people that are not sick at the moment and don't have either one of these. So instead of getting 21 out of 22, it's actually 16 out of 22. So yes, doing ORs in junior high was easy. Here you got to pay attention to whether you can be both at the same time or not. And by coincidence, I'm getting, oh no, I guess this is a slightly different answer. This was 772, 7272. This is just 727272. So 7272, except there's a 7 after that, so make this 2 go up to a 3. 7273. And now each one of these is correct. Oh wait, it says try again on that one. Did it not want to? It still does it. Okay, find the probability of a random place that has neither a runny nose nor a sore throat. Not and not 821. 21 minus 5 is 16. 16 out of 22. Neither a runny nose is 8. And this is 13. That's 21. Did I do the wrong one where they're both at? No, they're both at 5. Minus 5. And grand total is definitely 22. I'm not sure what's wrong with this one. Okay, so I'm doing the... Oh, they're just 1 minusing this one. That's weird. If you have a runny nose or a sore throat, and then you do not. See, they're doing like a complement. So... So is it just, I guess it's just this 5 right here. So this nor does not, it's not the same as an or, apparently, after all. So what they're basically trying to do is they're trying to do the not, the complement of this one. And if you do 1 minus, now that I see the answer, I can tell what's happening, but 1 minus 0.7727, this is how they're getting 2273. 2272, 2273, it's off by 1 place, but so I guess this is the wording of it. The probability of a random selection student has neither a runny nose nor a sore throat. So this neither is like not. So we don't have this case is what it's saying. And that's the complement idea, case 2 right here, where you do 1 minus it. So I was misreading it as I was doing not a runny nose or not a sore throat, which sort of sounds like that's what it wants, but apparently it doesn't. So sometimes you'll watch me mess it up, and then you can see what, sometimes maybe the wording's a little tricky too, but if you see me mess it up, then you'll know how to do this when you're doing your homework. So once you get part 3 done, just instantly 1 minus the part 3 answer. That's what they're trying to get you to do there. Maybe that could have been worded a little better. And luckily here, notice they did the totals for you, even though these are extremely messy numbers here. Sometimes they're nice enough to do the totals for you on the side and the bottom. So here's our grand total right here. Don't add the rows and columns if they've already done them for you. Otherwise you get like totals on top of totals, which is really meaningless. So part 1, the report is open and comes from Brooklyn. So you can have what kind of report is it on the top, and then where does it come from on the side when you're doing one of each. And we're going to learn more about ands later, but this is an and case. An and is when both of them are true. And that's the part that you normally subtract in an or when you can be both. So I want to go to open report and Brooklyn. Brooklyn is right here. Open report's the first one. You just go to where they meet each other. And the answer will be whatever 1,170 divided by the grand total is. 1,170, that's the spot where they both meet each other. And now divide by 14,518. Round to 4 decimals. Okay, 0805, but there's an 8 after that. So 0806. And I can't check this till the end. Sometimes they make you check part by part, and other times it's you got to answer them all and then check at the end. The report is closed, or, see, this is an or, the other one was and. The report is closed, or it comes from Manhattan. So whenever you get an or in one of these chart problems, see if you circle them, do the circles crisscross each other. If they do, that's what you subtract, is the spot where they crisscross. If you circle both things and they're parallel to each other, then there's nothing to subtract. So if we were to do Brooklyn and circle Brooklyn, or Queens, circle Queens, these two circles are parallel to each other. So that's a case of mutually exclusive. And then you would just add them up and that would be it. There would be nothing to subtract. But Brooklyn, I'm circling that. Or was this about Brooklyn still? Yeah. No, Manhattan, sorry. Manhattan, or the report is closed. So I'm circling Manhattan here in the middle of the rows. But closed reports is vertical this way, so they crisscross each other. So that means you want to add all the Manhattans, 41, 49, plus all the closed reports, which is 9869. Notice that's almost to the total already, not quite, but it's getting close to the total already. So this wouldn't be like a warning, oh no, I must have done something wrong because it went over 1. But it would be wrong to do that because they crisscross each other and overlap. You can be both at the same time. You can have a closed report in Manhattan. So this spot where they meet each other in the table, that's what you have to subtract. If they meet in the table by circling them both, that's the part you subtract, 3380. If they don't meet in the table, if they're just parallel to each other, then there's nothing to subtract. And then you divide by the grand total. 4 decimals, whoops. I hit subtraction instead of division. So 10,638 divided by 14,518. 7327. 7327. There's a 4 after that. And don't make this mistake where you're like, oh wait, there's a 5 after that one. Maybe I could use this 5 to bump this 4 up to a 5, and then after it changes to a 5, then I could use that to bump up to the 7. You don't get to do that more than once. So if you want to round where the 7 is, the 7 will either stay 7 or bump up to 8, and the only thing that matters is the next digit after that, as it currently is. The next digit after the 7 currently is a 4. That's not high enough to add 1, so leave it 7327. The report just comes from Manhattan. See, this is not an and or an or. These two are ands and ors. This is just a single basic probability. So Manhattan all the way across is this 4149 and just literally divided by the grand total. 4149 divided by the grand total. This is a basic or single probability right there. 2857, but there's an 8 after that, so make it 2858. The report does not come from Manhattan. See, this is what I messed up on the last problem. Once you get one answer, sometimes they want you to immediately do not the one you just did. So the one I just did is this 2857 number here. So I can just, you can 1 minus the answer, although here's another way to do it. Well, let me show you both ways. I can do 1 minus, and then, does it let me do history? Yeah, I guess this right here. Can I click on that? Maybe not. Okay, so 0.2858. 1 minus 2858. Or what I was trying to show you was, see, the answer is 7142. So if you, when I got the first decimal, whoops, I didn't type that right. 4149, see, I could tell something's wrong because it was an impossible answer. 14,518. See, if you get this answer and you 1 minus it, you can't just hit -1 really, because then it says it's negative and it can't be negative. But you could just hit the plus or minus button and get rid of the negative. Or another option is what I did earlier. If you want to, whoops, I keep typing that wrong. 4149 divided by 14,518. If you want to 1 minus this, but you already have this on the screen, one way to do it is to make it negative first and then add 1. That's a way to kind of backwards do 1 minus. Okay, 7142. 7142, which is the opposite of answer as part C. The report is pending. That's a single probability too. Pending is one of the top categories right here. The report is pending, so this is good over total, just these two right here. Singular basic probability. I'm doing the 178 divided by the 14,518. 0122, but there's a 6 after that, so make it 0123. 0123. Oops, where is it? Oh, it's down here. 0123. Whoops, I can't check it yet. Okay, one last part. The probability report is from Queens or the Bronx. See, they did this on purpose, too. I do these in class, too. Not every or, once you learn how to subtract something on or, it doesn't mean it happens every time. Queens or the Bronx, that's two different parts of New York. That's anytime you get two from the side or two from the top instead of one of each, then there's nothing to subtract. Queens or the Bronx. Well, Queens is the fourth row, and the Bronx is the first row. And if you circle both of those, they're parallel to each other, so you can't be both at the same time here. There's nothing to subtract here. You take the Bronx, the 2823, and then you add the Queens, 3421, and there's nothing to subtract. This is like junior high work other than the fact that these numbers are so large. But this would be a junior high case. They would only get this case where there would be nothing to subtract. So I added the two cases and divided by the total. This is like the baseball one where we were doing the sliders and the curveballs. There's nothing to subtract here. So anytime you get an or, you always got to watch out. Is this when I need to subtract something, or is this when I don't have to subtract something? And it all depends if you can be both or not. 4300, but there's an 8 after that, so 4301. And one of these is wrong. Okay. Does not come from Manhattan. And this one did come from Manhattan. Oh, I missed the decimal. See, there's a typo there. 0.7142. 100% sure that answer's right. I just didn't type it right. Yeah, see, it was just a typo on my part. So, yeah, watch out for little mistakes because that can cost you. This one, I was just misunderstanding what they were asking in that one part. But this one I would have had it right, but I mistyped it, and unfortunately in computerized homework, if that's your mistake, they don't give you any credit for that. At least in the homework you can correct it, but if it happens on a test, it's just unfortunate. Okay, so we're all done with 5-1 and 5-2. And this is still open, good. So 5-1, 5-2. You can work on this 02, 4-2 homework now anytime after you finish this. And then we move on to 5-3 and 5-4, 6-1, 6-2, and 6-3. And then there's a review. So we've got 2 out of 5 videos finished. We did a video for 3-3, 4-1, and 4-2. That was the first of the 5 of this unit. Then we just did 5-1 and 5-2 as the second one. And then the homeworks, the 0-2, 4 homeworks, you just do yourself. The third video will be 5-3 and 5-4, and then there'll be a fourth one, 6-1, 6-2, 6-3, and then finally a fifth one for the review. And the test is still almost 2 weeks away, so plenty of time if you're staying close to the calendar. Okay, so next video, well, I'll add these. We haven't really learned these. They did have an and in there, but it was kind of more just when they were both, where they both occurred. There's actually ands kind of work like the ors do. There's 2 cases of ands, and there's a simpler formula and then there's a more complicated formula. So that'll depend, like this one where this was about mutually exclusive or not. So we've learned 3 of the 5 types of probability, and the other 2 I'm sure are coming in the next 2 sections. And then we've done 2 of our 5 videos for this unit, and that's the end of this video.